So, yeah, I mean, as I was saying, thanks so much for the invitation. And I'm excited to have the chance to talk today about, some really cool stuff that me and a lot of collaborators have been working on both at U of T and elsewhere, on trying to map the Milky Way and in sort of the modern era of sort of large astronomical data sets, which often is shorthand today for Gaia, which I'll showcase. So let us jump right into it. One of the things I like to start out with is just to ask for all of you kind of what really is the Milky Way, and what does it mean to map it? I think on some level, this is kind of a question that we all kind of seem to intuitively know, which is that the Milky Way is the galaxy that we live in. That's kind of what we learn in textbooks. But, from an observational perspective, the Milky Way galaxy is just this. So we look out at the night sky for thousands of years. What we observed is just this band of material cutting across the night sky, and this is often what we refer to as the Milky Way, or at least what the Greeks referred to as the Milky Way. But this type of thing of sort of bright and dark bands, sort of that seems to cut across the center of the night sky, has fascinated cultures for thousands of years, all across the world. From stories of the Greeks, which is where we get our name of the galaxy from, to say stories from Japan, where it's sort of this river that separates sort of two foreigner lovers, to stories from sort of Central and South America, where the Milky Way is the spine that holds up the sky. This thing has captivated lots of us for as long as at least we've kept records. But we also know that this isn't really sort of the Milky Way as we refer to it now, which is the galaxy. That contains pretty much all the stars in the picture, not just the stars in the center. This is kind of what I think is the coolest version of this plot. And this kind of defines the scope of the talk by thinking of, this is taken with the Gaia space satellite, which was launched by ESA a few years ago and has been collecting data since, roughly the mid-2010s. And this is an all-sky view of the galaxy from what we can see in this kind of Earth-trailing orbit. And what you can see is tons of cool stuff. So lots of the dots that are on this plot are all stars inside our own galaxy. You can see sort of the same features of this bright spot near the center, where the stars get so dense that they kind of blend together into this, whole thing. These dark trails that we observe, those are all interstellar dust that's blocking the light that we observe. And you can also see some little friends. So this, for example, is like M31, which is the Andromeda galaxy, the closest other sort of large galaxy to us. And this is kind of the thing where, one question is, this is the Milky Way that we observe. But it's not the actual Milky Way that we'd like to see, which is we don't actually know what it really looks like. The same way, for instance, that the Milky Way galaxy is fundamentally, something that we live inside of, means that we can't really go out of it, fly out and say like a Star Trek style approach and try and look at it from the outside and take a picture. So we don't actually have the ability to do that. The same way that with the Earth for a long time, right? We were constructing maps of the continents and all these things for explorers across generations. None of us could actually leave the planet and look back on the Earth as sort of one unified whole and see kind of the picture that we all now see in textbooks today. That only happened in the 70s. We don't have the ability to do that with the Milky Way. And so other galaxies are sort of the only clues that we have to get some insight into the structure of our own galaxy from like a big picture perspective. So by looking at galaxies like M101, we can see that maybe our galaxy has like these spiral arms. You can see these dust lanes, this stars trapped at the center, all this type of structure. You see other galaxies that have these bars. You can see galaxies that have face-on views, edge-on views that showcase different types of structure. Galaxies that might be merging or have some other deformations. These are all like other ways to gain some insights into what our own galaxy looks like. By offering kind of these other mirrors into what's going on. And using all of that, we get this picture. And in this talk, I'll actually show you the data that underlies this picture that we have today. But this is fundamentally the artist's conception. So this is what we think the Milky Way looks like, but we don't actually quite know. And according to our best guess, sort of we are here, This is kind of where we think the sun is more or less located, kind of out in one of the spiral arms, about 8 kiloparsecs away from the center. But again, this is just our best guess based on data. And we definitely don't have a picture where we can kind of go up and like pin ourselves down on a map. So one of the fundamental questions that I'm really interested in figuring out is how do we go from kind of the data on the right, this two-dimensional data of all these stars in the night sky, and change that into this three-dimensional view of our galaxy to kind of do this cosmic cartography. This matters, I think, for three different reasons. I think it's just really cool. I'd love to see what our galaxy looks like. But from like a practical perspective, it's very interesting to understand our origins, right? What the Milky Way looks like today tells us a lot about how we got here, and also gives us some key insights into our place in the universe. We want to know kind of where the sun was born, how it's migrated over time, how the galaxy has grown up around us, and what that might tell us about the origins for life. That's also really useful when we're thinking about searching for life. Mapping out the galaxy requires understanding stars. We now know that stars and planet formation, all these things are a crucial ingredient for lots of life. And if we want to know where stars are born, where they've moved over time, what might be the most promising places to look for life, all these things do require understanding stars and more broadly understanding the galaxy. And the Milky Way is also this great laboratory for doing fundamental physics and dynamics. Things like galactic structure or actual ways that stars move can provide lots of clues to unanswered questions like dark matter. And actually, dark matter itself was discovered primarily through studying galaxies by looking at the rotation curves or the relative velocities of stars as a function of radius away from the center. And that gave us sort of the first insights that something was wrong, at least with the picture of what we understood about gravity, because stars weren't moving the way we expected. And so by studying galaxies in lots of details, there's some possibilities that we might be able to find more hints into the mysterious nature of things like this. So in this talk, I'm going to sort of hit 4 parts, although I'm going to kind of skip over one. The first is I want to talk a little bit about the history and background of what exactly this type of mapping has been in the Milky Way. The second is about inferring the properties of stars, which I'll mostly skip over since that's a little bit more technical. And then I'll sort of jump into some fun results about trying to understand the local solar neighborhood, using lots of these new data sets and techniques, and finally trying to come up with some cool visualizations for looking at the galaxy at large, at least as seen from the sun. So let me first start by jumping into the history, because mapping the Milky Way has a long history and extends all the way back to William Herschel. In fact, the first map of the Milky Way was constructed almost 250 years ago in Herschel's book on the construction of the heavens, published in 1785. Although the first mapping was done a couple of years before that. And this is the map that's shown on the right. And so, of course, the sun is at the center of the galaxy. And what you can see is every dot on this diagram on the right, that's a particular star that Herschel has used to kind of trace out the overall galaxy. And you'll notice that, a lot of this might not seem very accurate, but there's actually a lot of features of this map that are somewhat in line with the understanding of the galaxy today. So first, if you look over, you'll notice that it has this kind of pancake shape. In other words, there's more stars that seem to be along a particular direction than sort of going up or down. And that's interesting. And we know that a large part of that now is because the Milky Way is kind of this disk galaxy. So there are actually more stars in certain directions than others based on where we are. You also notice that there's this asymmetry. There's more stars to the right than there are to the left. And in fact, the number of stars kind of, you can see, just visually gets denser as you go further to the right. And that now we understand is because the galactic center is kind of in this direction on Herschel's map. And so it's somewhere off, over here. And we know there are more and more stars that are closer there and fewer stars in the outskirts, sort of on this side. And finally, you'll notice this big gap that's missing at the center. What's going on here? This is the first sign that there's some type of object or structure that's blocking a lot of light, that's preventing Herschel from seeing stars sort of in the exact center midplane of the galaxy. And we now understand that to be the signs of cosmic dust. And in fact, Herschel later became famous and did a lot of work on trying to understand the nature of dust. And that got him, there's this great telescope, the Herschel telescope, that was eventually named after him. It's done great work on this area. So how did Herschel do it? And what does sort of the successes and failures of his technique, propagate into what we understand today? So Herschel's idea was if you go look up at the sky, what you can just do is you can count the number of stars that you see. And he made two key assumptions here. The first is that all stars have the same intrinsic brightness. What that means is that if you have a bunch of stars that you see in the sky and some are brighter and some are fainter, that's because some stars are closer and some stars are further away. And so that gives you this proxy for distance. You can see, roughly speaking, how far away this one star is relative to another. So that gives you a handle on how far away the stars are. The second is this assumption there's no material between us and any other stars as well. So when you see things like, for example, this black, here that's blocking all that light, that's just because there are fewer stars there. This area is brighter because there are more stars. So that's like a real intrinsic difference in the number of stars. Or in other words, the density of stars that we observe on the sky is the same as the true density of stuff on the sky. Now I'm going to go into both of these assumptions because they underpin a lot of what we now have to do and kind of account for when we try and figure out the structure of the Milky Way today. So let's start with this one. So it turns out that unfortunately stars are not all the same. That would make life very simple, but they're still really cool. And in fact, in about 1910, two astronomers, Hertzsprung and Russell, essentially were the first to compile essentially a nice series of measurements showing that stars actually have a wide range of brightnesses and colors, but they're correlated. So the plot shown on the right is what's often called an HR diagram or a color magnitude diagram. And on the y-axis, essentially what you're seeing is brightness. So up here is brighter, down here is fainter. On the x-axis, what you're seeing is color. Essentially, left side is bluer and the right side is redder. The color of the actual plot is showing the rough density of stars. So things that are brighter have more stars, things that are redder have fewer stars, and the black points are individual observations. And these are all, again, taken from the Gaia space satellite, which has observed over 1 billion stars to try and estimate some of these quantities. So what you can see is that there is this really tight correlation between the brightness of a star and its observed color. If a star is brighter, then it tends to be bluer. If a star is fainter, it tends to be redder. And we understand this is now due to the fact that brightness correlates with the star's mass and temperature. The stars that are brighter are more massive, more luminous, and also hotter, and therefore bluer. And stars that are fainter tend to be lower mass, smaller, redder, and fainter. So one of the tools that we have to construct these types of maps is that we need an independent measure for the distance. And one of the ways that astronomers were able to do this is using a method called parallax. And this is the fact that we can, when you look at the same object from two different viewpoints, say a star here relative to this background, and you look at it from one direction, you see it in this case against a blue background, and from the other case, you would see it against a red background. And so if you look at it from the bottom, on the left, you'd see it could look like it's here. On the right side, you'd see it look like it's there. And this is like a cartoon, but this is actually what the Gaia space satellite actually does. And a lot of what constructed our ability to make these types of diagrams is we need an independent measure of distance to figure out what the true brightnesses of stars were. And what we do is we actually use the fact that luckily the Earth orbits the sun, which is great because I think otherwise we wouldn't be here. But we can actually take advantage of this fact that 6 months apart, the Earth is on one side of the sun over here, and then 6 months later, it swings all the way around to the other side of the sun, and now it's over here. And so what that means is that in January, if you're looking at a particular star relative to a lot of faraway stars, the relative positions of all these stars are slightly different. And this is great because this allows us to get an estimate of the distance. In fact, you can show that the parallax, which here we use this kind of weird symbol, this omega bar, is just 1 over the distance. And that allows us to infer the intrinsic brightness. This is great. So this is what gives us a handle on the intrinsic colors and brightnesses of stars. So excellent. That means that we have a bunch of stars whose properties we know, and we have one star that we don't know, say over here. So we have this unknown star, and all we know is it has some color, but it has some brightness, and we don't know what its distance is. We can just kind of draw a line and say, oh, okay, that means that if its brightness is there, but its color is here, then its true brightness must be somewhere in this bar, and therefore it must have some distance. So then we're fine. We can get some, estimate with some uncertainty of its distance just based on its color. The second part, though, comes in now, which is this assumption that there's no material between us and other stars, and that turns out not to be true. When we go and look out at the sky, what we actually see is all these dark spots, right? As I showed you earlier. And this is what we call the interstellar medium, or in particular dust. And this is just describing the fact that the space between stars, inner galaxy, and also between galaxies, just filled with things. Not a lot, but enough. And there are all these things such as gas, dust, and other materials that kind of lie between lots of stars. In particular, dust is important because while it's only about 1% of this interstellar medium by the mass, it scatters about 30% of all the light that's emitted from stars. And the diagram kind of showing this is shown here on the bottom. This is in galactic coordinates. So essentially this longitude down here is kind of in the plane of the galaxy. So when you go left or right, you can think of this kind of spinning around relative to the plane of the Milky Way. So you can go like 360 degrees, and looking up and down is kind of looking in or out of the plane of the galaxy. And just looking at this, you can see that there's, the dark regions are more dust and the light regions have less. It's just, there's a lot of structure here, and especially in the center, like around the midplane, there's just a lot of dust. So this ends up being a big deal when it comes to actually trying to map the galaxy, and is one of the reasons why Herschel didn't see any stars kind of in the central region. There's just too much dust there. Now, what dust does to light is it has two effects. They're called extinction and reddening. Extinction is just the fact that dust blocks light, like physically. Light's going to scatter off of it, and so it doesn't reach us. So this just means that things that are behind dust look a little fainter. This is kind of shown here on the left. In other words, things that are inside this cloud, you just can't see them versus things that are outside the cloud. The other effect that dust has is something known as reddening, which is that this effect, this extinction effect, or this scattering of light, is wavelength dependent. So dust is better at scattering blue light, which is kind of smaller and more compared to the size of these dust grains, compared to red light, which is a little less likely to scatter. And that means that more red light is going to make its way through than blue light. And because you're getting a little bit more red light than blue light than originally was present, relatively speaking, that makes things appear redder. So this is what you can see when you look at, for example, the edges of these clouds. The stars all get super red because they're getting blocked by dust. Or when you look in the infrared, you can see the same sort of effect, which is behind all this dust, you can see that it's a lot redder inside this cloud. So these two effects mean that dust has this weird confounding ability. So before, when we had a star, we said, boom, we have a color, we can assign a distance. What dust does is it says, no. You actually have a bunch of possibilities here. And another way of saying that is that there are two solutions. Maybe your star is red and faint because it actually is red and faint. Maybe it's a low mass star without much dust that's close by. Or maybe it's red and faint because it's actually a high mass star, one that's really blue and one that's far away, but there's just a lot of dust in front of it. So you get a lot of extinction and reddening, and that makes it appear like it's faint and red. And you get this additional problem, which is, at least in this case, you have this degeneracy between the type of star, which is that you can have stars with the same color, but two very different brightnesses. And these correspond to two distinct solutions in stellar models related to essentially whether the star is a dwarf, like the sun, so what we call, like, say, a normal star, versus a giant, like Betelgeuse, the star that's dramatically expanded, it's gotten huge, and therefore it's just much, much brighter. And so altogether, this means that we have a lot of uncertainties involved in trying to estimate the parameters of stars just based on images that we can see for all these things. And here's kind of the result. So this plot is showing the blue sort of shaded regions is the rough uncertainty or the estimates of a star's, foreground dust on the y-axis. On the x-axis is the distance. And so each of these different panels is highlighting a different star that we're estimating, and the red cross sort of shows our best guess. And what you can see is, just looking at these all look kind of gross. You have a lot of uncertainty where there's this really big uncertainty, for example, in the amount of dust. You have these possible multiple solutions that correspond to different types of stars or different positions in the galaxy. And this just means that when you're looking at data, it's hard to tell what type of star we have. In some cases, we get a good idea, but in others, we don't. One of the ways that traditionally we've gotten around this problem is by looking at masers. And masers are pretty cool. They're like lasers, but in the microwave. And they occur in nature in these really, really extreme star forming regions. So on the right is actually a picture of one of these. And I've highlighted this particular maser that's actually in the super dark region of all this dust that you can't even see. And the maser is kind of right here in the center where my pointer is. And these are super fun in the sense that because they are just kind of beaming a bunch of microwaves at us, they are super bright in radio wavelengths, and that means that we can measure very, very precise parallaxes to them. And because they're at such long wavelengths, we can see them through all the dust. We don't have to worry about it. So this is great. We can get really accurate positions to all of these. The problem, of course, is that it's very time-consuming to do this. For about 100 sources, we've required thousands of hours of observing time just to really pin down the distances to these things. But the result of all of this work is a map like this. This is now the state-of-the-art work led by Mark Reed at the Harvard-Smithsonian Center for Astrophysics. And what's shown here, all the individual dots are the positions of masers that have been measured using this technique. And it's now projection sort of top-down of the galaxy. So each of the different color points kind of shows the points that are associated with different spiral arm models. As you can see here, there's like a few. So we have like 5 spiral arms in sort of this representation here or so. And one thing that you can kind of see by looking at this is that this plot might look a little similar. And in fact, if I flicker back and forth a bit, you'll notice that it's actually, the artist impression is precisely based on this type of maser data. So it's pretty cool to see actually this is how the artist conception is made. It's using about these 100 or so maser observations, all of which have been collected this way. Again, in this very, very painstaking way, because using stars is just hard because we have all these uncertainties. But we're at the stage now with modern surveys where we have data on hundreds of millions or billions of stars. We have a lot of extra computational power. So we can start to think about how can we do better? I want to use these hundreds of millions of stars. I don't want to have to go to these really, really expensive observations of masers. They're rare. They're super time consuming. They're expensive. What can we do instead? Look at this image. In this one image alone, we have thousands, if not tens of thousands of stars that are sort of all possibly observable. They're super common. It's very easy to take pictures of the sky. Obviously, we can all take pictures with our own cameras on our phone, but taking pictures with a telescope has actually become really cheap as well. And that has given us data on tons and tons of stars, and now computing power is really cheap and faster than ever. So how can we actually scale up and use all of these stars? And this is kind of one really point that I've been very excited about, is developing a lot of methods with collaborators to try and do this. So I'm going to skip over all the details of how this happens, but the TLDR is that we are able to do it. And so we've developed some approaches where it can characterize all these very complicated uncertainties and all of this stuff, usually just in a few seconds per source. And that means that if we're willing to spend, hundreds of thousands to millions of CPU hours, we can start to think about analyzing large chunks of the sky using this type of technique. So in the next part, I want to talk about what we can do now that we have the machinery and tools and the data necessary to really think about using, instead of 100 masers, now like tens of thousands, hundreds of thousands, hundreds of millions of stars. And what are the cool science that comes out of it? One of the things that we're very interested in is trying to use them to understand things like star formation. We know that stars are born in these really dense and dusty clouds of molecular hydrogen. An example is kind of shown here on the right. This is a picture of the Orion Nebula. I love the Orion Nebula because you can actually go out and see it yourself, in the constellation Orion, like right below the belt. It's super cool. It's also one of these really active regions, star formation, that has tons of gas, young stars being born, all this great stuff. And studying these types of molecular clouds allows us to understand sort of the physics behind how stars like our sun may have formed. And that, of course, lets us wind back the clock and understand a little bit more about how lots of other stars have formed, and again, getting back to sort of habitability and life on other worlds, and sort of understanding our origins. The problem, of course, is that we can see these pretty pictures, but if we don't know how far away these dust clouds are, if we don't know their 3D geometries, it's hard to say like how big they are, how much mass they contain, and therefore like how efficiently are they converting kind of gas into stars. How is that chemistry working? How are those physical processes operating? So one of the things we want to do is figure out how can we get around this. And of course, this is where we kind of have one of the challenges of stars turn into one of the biggest strengths, which is that individually, there's a lot of uncertainty. You have these stars, they're all embedded in this interstellar medium, all this dust. So that's kind of a pain. But when you start combining them all together, now you can think about pooling all this information and saying, wait a second, when I observe these stars, I can actually see these spatial variations in their colors. And I can now combine these, essentially infer the distance and the distribution of dust from its effects on tons and tons of different stars. And so this is great because it means we can now think about using stars as kind of like these lighthouses that shine through the dust. And we don't really know where they are, exactly what their properties are, but if we have enough of them, we can average over all this uncertainty and do a really good job of mapping out the 3D structure of dust. And so this is one project that I did along with a collaborator, Catherine Zucker, who was at Harvard and now is at Space Telescope in Baltimore. And the idea was kind of straightforward. So here's an image of a cloud called Perseus. You know, a lot of these are based on kind of the constellations in which they're located, they're associated. And each of the sort of white area here is places where there's more dust. And so our idea was, what is going to happen if we take like a little pencil beam and try and cut through this cloud and ask what the properties of stars will be like along that particular line of sight. And so what we find is that if you think about this plot just like before, the y-axis is some units for dust, total dust, and the x-axis is some unit for distance. What we find is that there's some uncertainties, but there's going to be some stars kind of in front of these clouds, and they're going to have a little bit of dust. And then we're going to boom, we're going to hit this really dense region where a lot of stars are being formed. There's a lot of dust. And then afterwards, all the stars are going to be redder because they're behind this huge dust cloud. So we can include a statistical model. We can sort of try and account for all these uncertainties, for the fact that we expect there's going to be some variation. Maybe we'll get the answer wrong sometimes, but we can build up sort of a model to take into account all these individual facets of what it means to estimate distances. And so what's really cool about this is that this project, kind of building up all these pieces, is kind of uniquely enabled by this wonderful combination of these huge data sets, you know, increases in computing power and statistical inference, and turning it into all these wonderful data products that we can then use to do this type of stuff. So this is kind of the power of what I mean by age of Gaia, which is that when you have all this great data and you have all this computing power, you can do like super fun things that used to be impossible, you know, just 20 years ago. So one thing I can show is that I love making these interactive figures to really explore the results we get. So I'm actually just going to toggle over to that right now. So we made this fun interactive figure. We can send around the links afterwards, but you can sort of see this for yourself. I've preloaded a couple of these, but if you click on any of these individual cloud regions, it'll pull up a map of the clouds. And so here's an example of what this looks like for Cepheus, which is my personal favorite. So if you sort of look on the left, this tells you essentially your position and also how much dust is there. But what I love is actually looking on the right, where each of these individual pixels, you mouse over them, shows you essentially all the data we used, the results we find, our exact fit, which is kind of shown here in blue. And ultimately, this translates over to a distance, which is shown here on the top that you can kind of see. And what's great is you can actually see just physically that this cloud here is actually two clouds. There's one component that's kind of closer to us, which you can see here. But if you look down, there's actually a second component, and you can see that that actually occurs as well. There's this further component that has this distance that's much further away than the first. So this first cloud is somewhere around like 350 parsecs or 400 parsecs, and the second one is somewhere in the ballpark of like 900. So you have these two clouds that are superimposed on each other, and it's essentially invisible if you just look at the data on the left, but it's super clear when you look at our results on the right. You can also see our model is not perfect, in terms of estimating uncertainties and all these things, but it's pretty good in getting us a rough sense of identifying these two different structures. So there are tons of other examples you can click on here, but I just find that to be super fun. And you're welcome to explore all that for yourself, because we don't want to hide any of the actual science and data that we've done. We want all of you to sort of see and be able to judge for yourselves how you feel. So here's just an example of what that looks like. Now, you don't have to take our word that this works. When we compare, for example, the results we get from our method, which again is like this cheap method that uses all these stars that are publicly available and like super common, versus this other method, the masers, that are very rare but are really accurate, what we find is that our results agree essentially, almost perfectly within the error bars. And so we find really, really good agreement out to 3,000 parsecs, or in this case, roughly 10,000 light years or so. So this is exciting because this means that our results, which are much more widely applicable and available with a ton more data, we can apply pretty much everywhere. And we do. And this led us to some really, really fun stuff. So this plot is now showing this top-down view of the Milky Way. So now we can actually see what some parts of our galaxy looks like, or at least the extent to which we've been able to map it out today. So this is a map of dust. The sort of background images, the black and white scale, that's sort of a method of mapping out 3D dust pioneered by another collaborator, Greg Green, who's at MPIA in Germany. The sun is located here at the center, sort of right there. And this is again like this top-down view of our galaxy. And all the individual blue regions are places where we've applied our method. So you can think every single data point here has thousands or tens of thousands of stars that have gone into deriving sort of those results. And all of them have these names because these have been studied for a long time. One thing that we didn't expect is that when we looked at this data, we said, wait a second, what is this stuff that's right in front of our face? So we know, for example, about this local bubble, the fact that if you zoom in on like the region around the sun, there's not a lot of dust here. One thing we didn't expect is that when you zoom into other areas, that there's this long string of stars that all appear, or these star-forming regions that all appear to be correlated, kind of perpendicular to us, which is not what we expect. And it turns out that when you look at this in detail, we found this really, really cool structure that we call the Radcliffe wave. And so here's the same view of our data set, but now shown in 3D, where I'm just gonna actually mouse over some of this. What you find when you look at this from the side is that there's this really interesting filamentary structure to lots of these associations, which we've colored in red. In fact, here's our best fitting model. We find that it behaves really well like this sort of undulating filament, and it's over 2 kiloparsecs long, or over 6,000 light years. One thing that's super exciting is that this view of local star formation would have been pretty much impossible to do unless we had all these distances. They let us sort of bring all of this stuff into really sharp focus and redefine a lot of what we think about when we talk about star formation in the local solar neighborhood. In particular, it overturns this paradigm known as Gould's belt. Here's a model from about 15 years ago, and this little ring is how we used to think a lot of stars formed in our vicinity. And this was first proposed about 150 years ago by Benjamin Gould in like 1870. And so it's kind of cool that 150 years later, we've come across with these really nice data sets and much better models, and it appears that we completely kind of rule out this model as an accurate way of describing how stars are formed around the sun. So it turns out this is mostly a coincidence. So that's been super exciting and was very unexpected when we went about this project. Here's just another view of like the same thing, just colored in. So that's been fun. I think sort of shows some of the exciting possibilities of using these types of data sets and methods to tackle these problems. So in the last part of the talk, I want to sort of expand outwards a bit and think about how we can use lots of these stars to map the galaxy at large. What I've been doing before is kind of thinking about mapping these individual star-forming regions or these molecular clouds where a lot of stars are formed. We've primarily used that with dust. And that's equivalent to us saying that our sun is here. What we're trying to do is we're trying to probe structure by kind of looking at these regions and seeing how well they trace these spiral arms or other types of things around the sun. But there's no reason we have to limit ourselves. And the next thing that we wanted to see was what happens if we just look at everything. Why don't we just look at all the stars that kind of are in some vicinity to us and see what they look like? And so this is what we sort of did for our next step. And so we called this the Augustus project, Augustus being the first thing that happens after Brutus, which we thought was a kind of a dark joke. And so here's kind of what we found. So pretty much everything, there's some details for people who are, say, more astronomy savvy kind of in the corner over here. But overall, what the idea was we wanted to take 170 million objects and run them for about 1 million CPU hours. And there are two main caveats. The first is that we cut out the central plane of the galaxy, primarily because there is a lot of, give me a second. Primarily because there was a lot of complicated stuff there, and there's a lot of stars kind of in the central plane, so we just decided not to model it. And this pole that you see here is essentially the representation of the southern sky projected into galactic coordinates. So in other words, that's the stuff in the south. And we couldn't observe it because the telescope that we're using for this data is based in Hawaii. And unfortunately, we don't have an X-ray telescope that can look through the Earth. But it's very sad, but I think it's just another reason why sometimes it's so exciting to send telescopes up to space, where you can actually look at the whole sky in 360 degrees, except for the part that's blocked by the sun. So I want to emphasize this was just a fun proof of concept. And the idea was that if we can do well with 170 million, the next step is to actually try and do like 1.5 billion and then see where we can go from there. So here's a sort of demonstration of a little bit of primer. That's what I'm about to show you, which is we can think about taking a little slice, and this is a 2D version, but you can think about taking like a little sphere and kind of cutting out a shell around the sun and saying, you know, what are the stars doing in kind of this particular shell? If we do that and we project the data down, here's kind of what we get. This is a demonstration sort of showing this visual interface here. And what's shown in the color scheme is essentially the number of stars. And you can also see if you zoom in, essentially there are some little arrows kind of indicating the direction of motion based on other observations by the Gaia spacecraft. So what you can see pretty clearly is that there's this distinction. There's a lot more stars kind of in the central region, but there are stars that are kind of on the outskirts. And this division between like the disk of the Milky Way versus this broader halo component, this spherical, you know, small number of stars that are kind of orbiting around the galaxy in kind of a shell, you can kind of see this very clearly in the data, which is cool. If we go a little further out, you can see some more stuff. So here's an example where we actually look towards the center of the galaxy on sort of close to 0, 0. On the outskirts here, we're looking at this region up here, the anticenter, so really, really far away. And when we do this, we can see this really clear evidence. For example, you know, there's a lot of stars near the galactic center, that's no surprise. But you also see this really coherent motion and this overdensity of stars far away. And this is essentially what's known as flaring of the disk. The fact that rather than kind of taper off and be smaller, as we go further away from the galaxy, we actually get this inverse effect where the disk gets kind of puffy and really big as stars orbit. And this is due to a lot of dynamic effects. But you can actually see this really clearly if you look at the velocity structure. So you see that all these stars are kind of engaging in this very coherent motion where they're all orbiting in the same direction, you know, similar to like these circular orbits in a disk. It just happens to kind of get really puffy. So this is kind of the really exciting things you can do when you're trying to look at our galaxy this way, is using all these stars, you can really help to elucidate these types of structures really clearly. What I want to kind of end on here is this fun visualization that we were developing, which we're calling All Sky, which tries to bring sort of the same innovations that people use to construct kind of like these wind maps or weather patterns here on the Earth and try and see what we can do with them in space. So that's what I want to sort of end with in terms of fun demos. So what you're seeing here, which hopefully is coming across okay in the video, is essentially this projection of the sky, but now in this interactive format. So if you can see some of these lines of motion, these aren't really the motion of individual stars. These are more like stellar currents. You can think of them as like bulk motion of many stars, you know, kind of visualizing the general flow for illustrative purposes. And so if you click around, this is all interactive. So you can see it tells you where you are. It tells you the direction of motion, how quickly it's going. And you can also change like the background color. And just looking at this, for instance, right, you can see there are these specific regions where, for example, relative to the background, stars seem to be moving in like a very coherent fashion. And these often do correspond to particular signatures of, say, clusters of stars that are moving in a very particular way. And so you can kind of see that just can pop out of this data. One thing that I find really exciting, though, is that this is a projection. There's no reason in an interactive figure we have to limit ourselves to a 2D version. And I love looking at an actual sphere, since, you know, that's what the sky looks like to us. It's a nice, you know, a nice sphere that we're actually looking around on. So this is, again, sort of this slice of stars in this particular distance bin, the same one I was showing in the slide. And now when you sort of, you know, look around and pan over the data, you can see, okay, it makes sense that, for instance, we're missing all this data in the south. You know, it kind of shows it very clearly in the model now. And you can sort of see lots of this structure. We also made it so you can change the background, so you can see the density of stars, and this lets you see, for example, all these dust features, these particular stellar features you can see earlier kind of show up as these overdense regions where there are a lot of stars relative to the background. You can look at the chemical composition of stars, which we estimate, as well as their ages. And one thing that I love is actually being able to, for example, find new and cool things. So one that I really enjoy is if you look in the south here, you'll see that there's a bunch of stars kind of orbiting in the circle. These are stars orbiting in the disk. But there's this extra stream that's kind of cutting across through the bottom of the channel and kind of coming across the other side. And what this whole thing is this is actually a dwarf galaxy known as Sagittarius, which has collided with the Milky Way and is sort of on, I think, its second pass through. And so what we're seeing is all this debris that's kind of been strewn about in the wake as this galaxy has plunged through the Milky Way and has come around the other side, as it's kind of slowly getting swallowed up and sort of turning into part of the halo that we observe. And this has been well studied. It has tons of cool features in terms of how the disk has behaved and recent star formation. But you can just kind of see it very visually looking at this type of plot. And this is the type of exciting thing where we're really, we are very much looking forward to thinking about how can we visualize kind of these 1 billion stars in the future. And my dream, at least, is to have some really cool, like, augmented reality thing where you can kind of swim through and see these different lines of motion and zoom in on given regions and change all these backgrounds to figure out, to look for fun structures and really see all this stuff in 3D the way that it's really moving in space. So that's kind of like a really fun element. And so that's kind of where I want to end is showcasing, the real power, and I think just how cool it is that we can now do this type of stuff. And so, I just want to conclude by sort of summarizing that I talked a little bit about some of the history, about how we kind of got here and why we care about trying to map out the galaxy all the way from Herschel, 250 years ago to now. I skipped over sort of the statistical details, but I'm happy to go into some, additional stuff if there's any questions about how exactly we do this. And I highlighted, we combine all this information and try and map out like local star formation using these dust clouds. We found some really, really exciting stuff that we didn't expect. And finally, hopefully you all enjoyed, our attempts to visualize kind of the hundreds of millions of stars that we see on the night sky, and try and put it together to really get some, at least limited picture of what our galaxy is doing. So our hope is that in the future, as we continue to scale up to more stars and the data gets better, we'll really be able to come up with this very exciting, interactive 3D picture of our galaxy that all of us can explore together. So that's essentially where I want to end, and I'm happy to take any questions, or if we're out of time, thank everyone for coming.
Okay, thank you so much, Doctor. So if anyone have questions, they can put in the chat and I can forward them to Dr. Speagle. Everyone, please try to be a bit respectful. It's appreciated. Yeah, so if anyone has any questions, they can put it in the chat. By the way, Doctor, those were really nice graphics. Yeah,
especially I'm glad you liked them. It was a lot of fun to make. So,
so we have a question. Secretary is asking for the graph in the bottom corner. There seems to be missing data. Why is that? Is it related to the location of the telescope used?
Yes, excellent question. So that's right. So there's two places where we're missing data here. The first is data that's missing in the center, so this region, and we're missing this essentially because we chose not to model it. There are just a lot of stars kind of in the center. There's actually more stars in this small strip than there are everywhere else on the sky. So we cut them out kind of to keep this project manageable, but there's tons and tons of stars here, and our next goal is to fill them in. The stuff on the edges here, so things in kind of this region, this is because the telescope we're using, unfortunately, it can't see in the south. And so we just don't have data kind of in this particular regime. However, our next goal is to actually use data from Gaia, which is an all-sky survey, and so we'll be able to see everything across the entire night sky and fill in all these missing regions. So our hope is that in like the next year or so, we can actually fill in lots of this and release like an updated version of this map with 10 times as much data and looking hopefully even better. So hopefully we can all stay tuned.
Thank you. Caleb's asking, will advancements in mapping the stars in the galaxy primarily come from advancements in telescopes that are better than Gaia, or rather than from statistical or computing power advancements?
Oh, this is an excellent question. So I'd say it's a little bit of a combination of both. There's actually a third element there as well. So one is that we do expect that, so one telescope that's coming online soon is going to be the Rubin Observatory. And that is going to essentially be taking really, really good data across a bunch, essentially over most of the, ultraviolet kind of to the near infrared. And that's going to give us wonderful data over, again, not the whole sky, but a decent swath of the sky. And it's going to be a big improvement over the data we have now. So when combined with Gaia, we're really optimistic that will improve the estimates, lots of these things. The statistical methods are also something that we're working to improve. Right now, we've done a lot of work to get these to be pretty rigorous, but there's more stuff that can be done to actually figure out ways to incorporate some levels of uncertainty better, to incorporate lots of information about the galaxy as a whole into our modeling. And so that's sort of one of the next steps for us. One area actually that we expect that there will be a lot of progress recently that I didn't talk about as much is actually improvements to the models. So one of the biggest sources of uncertainty in lots of this is the fact that our stellar models actually are not quite accurate enough anymore to really cope with the quality of the data that we observe. So there's a lot of effort now to actually improve those to make sure that they can reproduce the data better. And hopefully, if that can happen, then we'll be able to substantially improve sort of our uncertainties and our distances to lots of these things to make that better. So I'd say it's a combination of all the above, plus additionally, we hope that some additional advances in like sort of theoretical models and these simulations are going to really help take us that extra mile.
So it's 6 o'clock, and I think it's a good point to end the talk. If anyone has any last minute questions. Okay, I would like to thank from everyone to Dr. Speagle for giving such an amazing talk, and thank you so much, Dr. Speagle, for your time. And again, sorry for the earlier incident, and I'm sorry if it caused any inconvenience to anyone. Thank you so much for attending the talk. Hope you guys have an amazing weekend, and happy Halloween.
Yes, no, thank you everyone so much for the invitation and for coming, and also apologies for some of the issues, and hope everyone enjoyed the talk and has a wonderful weekend as well. So thank you so much.